Well, that introduction is really troubling because I'm responsible.
People were wrong. You know?
Yeah, my record of being wrong is. Well, this is one more opportunity. I could. Let's see, I gotta get used to these boards. I could make a list. I think it's also already true that by the time I got to know Nima, I was worried about supersymmetry. I think in fairness, I could say that. But I've been wrong about lots of things. I was wrong about neutrino masses. I was wrong about lots of stuff. So we may be wrong today about, and I've been around enough to have been wrong about many things. So let's see if we can just. Oops, here we go. So I'm going to, so I'll try and be careful. Okay, so I'm going to talk about the strong CP problem. Okay, and I'm going to talk about various proposals to solve it. Okay, so let me just remember what I called this. So we've called these lectures the strong CP problem and its implications. And probably this is a safe title from the perspective that Nima just set out, in the sense that there probably is a problem. Okay, I'll talk about that too as we go along a little bit. To what extent, some people don't worry about it too much as a problem. To what degree is it a problem? But it looks interesting. It looks like something we should be able to figure out, okay, and whose solution we ought to be able to get. And we have a few ideas for what these might be. Okay, so in these 3 lectures, my first lecture today will actually just be to introduce the strong CP problem. Okay. In the second, can people see, by the way? Okay. In the second lecture, I will talk about some proposed solutions. Okay, well, there are roughly 3 categories of solutions, but again, this is perhaps an opportunity of some kind for people. Perhaps there's something else, or perhaps something different one can do. And when I do that, I'm going to also provide some assessment. Okay, and this is in the category that Nima talked about of, I'm going to throw my prejudices out at you. Okay, and with this caveat that my prejudices have historically largely been wrong. Okay, and then and in the third lecture, I'm going to focus mainly on axions. Okay, and the questions I'll ask there will be how the axion might arise in some more fundamental way. Why is the axion plausible or not from some more fundamental perspective? And so I could here put origins. And I'll also focus a lot on cosmology. Okay. And in that lecture, I'll also talk about detection, though Peter Graham will tell you much more about experimental proposals to discuss those and to explore axion, to look for axions, he'll tell me much more about, and in particular, he'll tell you about proposals, really things that are truly new, of which he is partly responsible, for which he's partly responsible. Okay, so to start this subject, the strong CP problem is a problem of the strong interactions. It's a problem of quantum chromodynamics. And just to remind you, the Lagrangian for quantum chromodynamics is something simple. So I like to write it like this, minus 4g squared fu nu squared plus q bar I d slash minus m q. Okay, so here, okay, I've got a term for the gauge fields. I've got a term for the quarks. Here the quarks or whatever they are. It might be, for the most part, today I'll talk about 3 quarks, U, D, and S. Okay. And I'll switch back and forth. Okay, so this may be a little unnerving for people. I'll switch back and forth between left-handed and or 2-component fermions or 4-component fermions. And I'll try and tell you which I'm using. And basically, just because so you shouldn't be afraid of either. And I have a distinguished colleague who's written a whole review of 200 pages on 2-component fermions. But I think, but sometimes 4-component fermions are easy to work with. Sometimes 2-component fermions are easy to work with, especially in cases where you have a mass. 4 components are often easier to work with. Without masses, 2 components are often easier to work with. Okay, and I say I'll switch back and forth. Okay, so F mu nu here is the field strength of QCD. Okay, and so sometimes F mu nu I can think of either as a set of objects A equals 1 to 8. Okay, or I can think of F mu nu. Sometimes I'll think of F mu nu or A mu as a matrix. Okay, so some Hermitian traceless matrix. So now this theory is remarkably successful. Yeah, I'm going to be unhappy. Okay. These boards are a little intimidating here. Okay. Okay, so one of the things we learn about in our textbooks is we learn, because it's something kind of straightforward to study, is the high energy or short distance behavior. Okay, and whatever disappointments we may feel about the Large Hadron Collider and its failure to discover supersymmetry or composite Higgs or whatever we're hoping for, this element has been just one striking success after another. Okay, so this part of the story is very well established and is in fact an important backdrop to the Higgs discovery. Okay, so this part's okay. And of course, this is related to the property of asymptotic freedom of this theory, the fact that the coupling constant at high energies is small. Okay? The other side of that is that long distance physics is hard in the strong interactions. Okay, and we have a variety of tools. The tools include historically using symmetries of the theory, and we'll review some of that. But in reality, the really important thing in the last 2 decades has been the successes of lattice gauge theory. Okay, so in lattice gauge theory, you replace the space-time continuum with a set of discrete points. Okay, and the path integral there becomes just an ordinary integral. The path integral here in Euclidean space. So this is integral dA mu e to the minus s, and with the other fields as well. That path integral becomes an ordinary integral. Integral just over fields at every space-time point, at each of these discrete set of space-time points. Okay, and what makes it hard is there are lots of variables. Okay, to study this problem, one uses statistical techniques, so-called Monte Carlo techniques. So I'm probably also, old enough that I also, not only was I skeptical about lots of experiments, I was probably skeptical of people's ability to do this, but the state of the art is quite remarkable. Okay? And so right now we know from lattice gauge theories, we know the basic parameters of this Lagrangian. So first of all, I should have said this mass here is a matrix. Okay, so M is mu, md, ms, just taking it to be diagonal. Okay, and we know these numbers. We know that mu is 2.18 MeV. Okay, md is 4.68 MeV, and ms is 90, I can't read my notes, 93.5 MeV, where the errors here are all sort of at less than 10%. Okay, so the errors, the quoted errors, just, and this you can look up in the particle data group, the errors are less than, are at sort of the, at the 10% level. But I should tell you something else. Okay, so when I tell you this Lagrangian, one of the first things you learn when you encounter this Lagrangian is I have to tell you how I define it. Okay, this Lagrangian is subject to renormalization. Okay, and I have to tell you what the scale is at which I define this theory. And I have to tell you pretty precisely how I define it. The people who tell you these results in lattice gauge theory tell you that these are the results, these are the masses in the so-called MS bar renormalization scheme, which you've probably encountered in your field theory textbooks, at 2 GeV. Okay, so there's a really quite precise statement about what these masses are. We don't get to, we'll talk as we talk about solutions of the strong CP problem, we'll focus, for example, on this mu. Okay? And we don't get to take out mu and put it on a scale or something. We have to get at it by these rather indirect means, and we have to give very precise definition of what we're talking about. Okay? Lattice gauge theory also, in fact, is one of the sources of the value of the strong coupling constant itself. And so, for example, the lattice gauge theorists quote alpha s mz. They don't measure it at mz. They measure it, of course, at lower scales and then run it up. But they quote alpha s of mz is 0.11, is this right? 92, plus or minus 0.0011, okay, which is in quite good agreement with other measurements that come from high energies. So, at the high, so kind of at the very high scale or short distance and at low scales, we are in pretty good control of this theory. Okay? So, again, it's remarkable, and it's in the spirit of things I would not, 25 years ago or something, I don't think I would have imagined that people would say things with this level of reliability. Okay. Okay, so I said that lattice gauge theory is one tool we have, and another is just to think about symmetries. And so let's think about the symmetries of the Lagrangian. Okay, and here it's nice to think in terms of two-component fermions, and the reason is, in this case, again, for 3 light quarks, and we see here that indeed we have 3 quarks that are relatively light. The strange quark isn't all that light, but it's still, it's lighter than other hadrons. So with 3 light quarks, the Lagrangian has a symmetry. Okay, now in terms of these two-component spinors, okay, the Lagrangian has a symmetry which I can call U3 cross U3. okay, under which Q goes to U Q, where U is a U3 matrix, okay, and Q bar goes to U Q bar. Okay, so each of these, V Q bar. Okay, so each of these is a U3 matrix. Okay, so this is sort of the symmetry at the classical level. All right, so I should say three Lie quarks. I should be a little careful. If I neglect the mass, so of course it doesn't have this symmetry with the masses. This is if I neglect the mass. Okay, the mass term itself, the Q bar MQ. In fact, I could put here. Let me write this differently. Let me put the V over here. Okay, so Q bar MQ, the mass term breaks the symmetry. All right. In fact, I'm going to do one more thing just because it'll make it nicer. I'll put a dagger here. Okay, so I'll take that as my transformation law. Okay. So now, I guess we should go over here. Yeah. Okay. So this, how is this symmetry realized? So we'll call these symmetries the chiral symmetry. Okay, so the spectrum of QCD doesn't fall into nice multiplets of this group. You don't learn about something this complicated in the spectrum. Instead, the symmetries are spontaneously broken. Okay, so what do I mean by that? I mean that SU3 cross SU3 is broken by something. What's the order parameter? The order parameter for this is the expectation value of Q bar Q, and I'll put some indices on here, Q bar F, Q F prime, which is some number, C, times some QCD scale lambda cubed times delta F, F prime. Okay. Now, again, this is something we've said in some form or another since the 1960s at least. Okay, for a long time people have known something like this. And again, going back to this lattice gauge theory story, which I described up here, we actually have numerical evidence that in fact this sort of picture holds. Okay, and again, that's remarkable because this kind understanding these chiral symmetries on the lattice is quite a challenge. Okay, so so this breaks the symmetry. This breaks the symmetry down to diagonal subgroup. Okay, so basically in terms of these transformation laws, okay, the unbroken symmetry are the set of transformations with U equals V. Okay, okay. So this is vector SU3. You can call it SU3V. It also preserves a U1. So I can just put that here. Let me put that like this. So I'll call that U1B. Okay, so there's a U1. Okay, and the remaining symmetries are spontaneously broken. Okay, so in the SU3, so we started out here with U3 cross U3. Okay, U3 has 9, SU3 has 8 generators plus 1 for U1. So altogether, there are 18. Okay, we've broken that down to 9, so we have 9 broken generators. Okay, and so there should be 9 Goldstone bosons. Okay, and so what are they? Okay, well, we identify those. It's actually interesting to think how much history, especially the ancient history of this subject, happened here. But anyway, but there are 8 of these. Okay, so these include the pi plus, pi minus, and pi 0. Okay, there are the k mesons. Okay, so k plus minus, k0, and k0 bar. And the eta, that's 8. Okay, and the problem or the puzzle for a long time in QCD was where's the 9th? Okay, so okay, so the 9th, okay, if you've got to go through the particles in the particle data book, the 9th, the only candidate you'll find for the 9th is a particle called the eta prime. And I mainly just want to remember its mass. Okay. It's gone somewhere in my notes here, sorry. Yeah, here we go. Okay. So the eta prime, we could put a question mark by that. The eta prime has a mass, m eta prime is 958 MeV. And that's opposed to all these other particles. Okay, so the pi's don't have much strangeness. So okay, maybe it's not so surprising that they're not so light. But the eta prime, but the eta, which does have strangeness, has a mass which is about half that. So m eta is 548 MeV. Okay. And remember that in a relativistic field theory for scalars, for bosons like these pseudoscalar mesons, okay, the relevant mass parameter is really not the mass, but the mass squared. Okay? So this mass is about 4 times larger than it ought to be. And you can make that more precise. But this mass of the eta prime is large. Another way, as I said this, if I had said, oh, well, the S isn't light, the strange quark isn't so light, maybe I shouldn't think about that. But then I would compare, for example, I might compare again, the mass of the eta in that case with the masses of the pi mesons. Okay, so again, there's a puzzle. Why is this particle? Why is this particle why isn't there this lighter particle? So. Yeah, I think we remember where we're going, so. Okay. So what might account for this? Okay, so so we're worried about one current, a current for which there isn't an associated Goldstone particle. Okay, and I'm going to write this current in a 4-component language. Okay, so I'll call this J mu A. Make sure that's what I called it in my notes. Now I'm going to call it J mu 5. Okay. So the 5 refers to the gamma 5 that will appear in the current. Okay. And this is equal to Q bar, gamma mu, gamma 5 Q. Okay, so now I'm switching back to a 4-component notation, just because, again, it'll be somewhat easier in computations. Okay, and what's interesting about this current, so classically, partial mu J mu 5 is proportional to things involving, actually, I can write it. It's some, in fact, I can write it as Q bar M gamma 5 Q. Okay? So it's something that vanishes in the limit that the quark masses go to 0. Here again, this mass is that mass matrix I wrote up there, this mu md ms. Okay? So this current classically is conserved in the limit that the quark masses go to 0. Okay? But it has an extra piece, okay, a piece known as the anomaly. Okay? And here I have to warn you that for factors involving theta and anomalies today, the factors of 16 pi squared are impressionistic. There are often 2's missing, and I can make excuses that it's whether I take the trace of FF dual or whatever. But if it matters to you in any computation you do this week or in the near future, make sure you get these numbers right. Okay, so I'd hate to think you may, well, anyway, what can I say? I would hate to be responsible for some catastrophic factor of 2 error.
Thank you for relieving the rest of us from having to.
No one else is. No. My colleagues are much. Not only do they guess better, but they also get factors. When I have to, I get factors right. But I'm afraid. Okay. So we have a piece here, 1 over 16 pi squared FF dual. FF dual is again. So I should tell you what FF dual is. So F mu nu is the field strength of QCD. Okay, it's the thing we encounter. And F mu nu dual is a half epsilon mu nu rho sigma F rho sigma. Okay, and basically what this is, again, here I'll now get signs wrong if I do it, but basically F and F, the dual fields are related by the exchange of E and B. One of them with a minus sign. So again, like the factors of 2, if I have to think, I'd have to think for a second to get the minus signs right. Okay, so epsilon mu nu rho sigma is the totally antisymmetric symbol involving 4 indices. Okay, and so I think, let's see, are we okay here? Yeah. Okay, so there are a couple of responses that you might have to seeing this thing. Okay, so one thing you could say is, oh, great, the current's not conserved, end of story. I don't have to worry about why I don't have this extra Goldstone boson. Okay, but alternatively, you might say, let's look at FF dual. Let's do it first in the case of a U1 theory. So for U1, FF dual is a half epsilon mu nu rho sigma, okay, F mu nu F rho sigma, okay, and that's equal to, if I just write this in terms of my gauge fields, this is a half vector potentials epsilon mu nu rho sigma, and I have d mu a nu d rho a sigma. And then because of the antisymmetry of epsilon, I can pull this d rho over here. I can pull the d rho out. Okay, so this is a half epsilon mu nu rho sigma. Actually, let me pull the d mu out. So I can write this as d mu a nu d rho a sigma. Okay, I've added a term here. Okay, a term that involves 2 derivatives on this a sigma, but because of the antisymmetric symbol, I might be tempted to say I can throw that away. Okay, and so what I learn is that this object, this FF dual, is d mu of some object k mu, of some current k mu. Okay, and so now looks like I'm kind of back in the soup because I can define a new current. In this case, J mu 5, so let's put a hat over, a twiddle over or something, is J mu 5. So J mu 5 twiddle is J mu 5 minus K mu. Okay, and that object looks like it's conserved. Okay. Now this has a generalization in, here, yes, in non-abelian theories. Okay, and this I'll leave for you as a little homework exercise. Okay, and I should say, by the way, I will post my notes. So the homework exercises are there. I've set up online things. You'll be graded. Okay. Those who know me well know that my capabilities are not that high for automated education. So anyway, but in any case, let me write down what K mu is in this case. So K mu is now epsilon mu nu rho sigma. It's got to be something that reduces in the case of, so this is A mu nu F mu, oops, I'm writing out, F nu rho B, A, I'm sorry. So this is the gauge index. These are the Lorentz indices, minus 2/3 FABC A nu A rho B, A sigma C. There's something wrong with the indices in my notes. Okay, but this generalizes this previous statement and allows me again to write down a conserved current, okay, in the case, something that looks like a conserved current. So I can define a conserved current. Okay. Now, at this point, especially when you stare at it in this form, you might be suspicious. Okay? Why? Well, this isn't gauge invariant. It's got these A's in it. Okay? And if you think about the way we usually think about conserved charges in the presence of a conserved current, the way we see this in our first E&M course or what have you, okay, what we usually say is we look at our current. So we look at, for example, d4x d mu j mu. Okay. And we write this as an integral over some surface. So this is, say, over some volume. This is over some surface. D S n mu j mu. Okay. And then we always say, everything falls off at infinity. Let's not worry. Okay, we'll throw this away. Okay. But in fact, we could be suspicious here, as I say, and we'll see this in a moment. We could be suspicious because the A's themselves, not being gauge invariant, may not fall off that rapidly. And what we'll see is, for example, even in a semi-classical treatment of this theory, there are configurations where the vector potentials fall off as 1 over r. Okay, and this surface term is not negligible. Okay, so the surface term falls off like 1 over r cubed. Okay, and receives a non-vanishing contribution. Okay? So there's something different between the abelian theory and the non-abelian theory. I should say that if you hang out with people around the institute, okay, you'll even worry about the abelian theory, because in the abelian theory what I assumed is that the order of derivatives doesn't matter. Okay? That's not even necessarily true. Okay? It's not true in the case where you have, for example, a magnetic monopole. Okay? So this theta, so this current, this object that I wrote here, can be important in a variety of circumstances. So, let's see how I do here. Okay. All right, so let me say a word or two about, well, yeah, okay. So what are so we're now ready kind of to announce this strong CP problem. Okay. So far, okay, I'm going to try and convince you in a few minutes that really these kind of configurations are important, that there are configurations in the path integral for which this current is really not conserved. But let's even just assume that that's the case. I mean, at this point in time, I can, when I want, I can invoke, I can say, well, lattice gauge theorists have shown us that it's okay, so it must be true. Okay, but we'd like to understand it in some more qualitative way, some more conceptual way. Okay, so let's Okay, so let's think about sort of what are the consequences of this assumption. So let's assume, okay, that this current J twiddle is really not conserved. Okay. Or equivalently, that integral d4x FF dual is non-vanishing, has some real consequences for physics. So this is the thing that breaks this symmetry. Okay, so the flip side of that is that then, okay, I can add to the Lagrangian a term L sub theta, okay, which is theta, so let's call that delta L, is theta over 16 pi squared, integral d4x FF dual. Okay. This is a term which I might have ignored as a total derivative, okay, but now I say I can't. Okay, and this FF dual is 2 E dot B, okay, where these are now the electric and chromomagnetic fields. They carry an index A, okay, if I write them as I said before, as I write them with these indices, or there's a trace if I can think of this as trace, F mu nu dual, if I think of these as permission matrices. Okay. And what's interesting about this term, or significant about this term, is under charge conjugation, this is even, okay, since E and B are both charge conjugation odd, okay, but under parity, E flips sign and B does not. So this violates CP. Okay. All right. Now, one of the things certainly people in my generation kind of learned in school is that the strong interactions preserve CP. Okay. So this looks like a sort of a red flag, okay, and this is in fact the strong CP problem, the fact that we can add this term. Okay, now I'll do I'll make some more precise estimate in a moment, but basically you can ask how would this show up? And as I said, we're going to be because we know that because we've assumed that we've solved this problem of the missing Goldstone boson. Okay, we're also able to explore what are the consequences of this, and this we can explore using the chiral symmetries of the theory. Basically, plus the supplemental statement that there's no light Goldstone, there's no light pseudo-Goldstone particle for this extra current. So using the chiral symmetries, we can calculate things, and one of the things, well, we can calculate things which we can't observe, but the thing that we'll calculate in a little bit is we'll calculate the electric dipole moment of the neutron. Okay? This is like a term in some kind of effective action for the neutron, which looks like n bar, so n, sigma mu nu, I'm sorry, and F mu nu dual. Okay. So we're used to writing down, thinking about magnetic dipole moments. So if magnetic dipole moment, we wouldn't have the dual here, and this would be a piece that would look like sigma or S dot B. Okay, but as I said here, I've replaced the E and B. Okay, this is a term which for a slowly moving neutron looks like S dot E. Okay, so it's a term which describes a coupling of the spin to the electric field as opposed to the magnetic field. Okay, And this is something people have looked for forever. Okay, so we've set, Nima set various standards for time. Okay, this is even well before my time. And we know that this neutron electric dipole moment is very tiny. And I'll talk about that again in a few minutes. Okay? Okay. There's no gamma. I'm sorry, yes. There's no gamma mu and no gamma 5. Thank you. Okay? Okay. And, well, this actually sort of works in either 2-component or 4-component notation, so I won't even specify. Okay, especially without the gamma mu. Okay. All right. Okay, so this thing is known, so we'll turn this into numbers. What we're going to learn is theta is less than of order 10 to the minus 10. Okay? It's something we know reliably both from experiment and from our understanding of theory. Okay? And I should have said here that this theta here, FF dual has a mass, dimension 4. Okay? So theta is a pure number. Okay? So we have a pure number, okay, which has to be extremely tiny. Okay? And we'll talk more, I say, about what the significance of that. Okay, so what I'd like to do now is I'd like to spend a few minutes sort of convincing you that this extra term is important. And probably good to do. Let's do it here. Okay. And what we're going to do here I should say this is important probably for your general education, and it will be important also in the third lecture. We'll actually use some of these techniques in a reliable way. But what we're going to do is we're going to think a little bit about this kind of functional integral I described. And we're going to think about how this extra term, this theta, might be important. So I'm going to discuss now a topic known as instantons. Okay, and I'm going to explain, so many of you probably know what these are. For those who don't, I'm going to explain a little bit what this is about. So what I'm going to do, I want to think about the path integral, so this Euclidean path integral. Okay, and for a moment, I'm going to not do all of QCD. I'm going to look at just a pure gauge theory, just a theory with gauge fields. Okay, so I'm interested in some integral dA mu e to the minus s. Okay, and maybe some operator here whose matrix elements I'm evaluating. Okay, and what I'm going to look for is I'm going to look for stationary points of the effective action, or stationary points of the action. Okay. So the spirit of that is going to be that S is going to be some classical piece, and I'll put it here 1 over g squared times some number. We'll figure out what that number is in a moment. Well, in fact, let me just cheat and say what that number is going to be. That number is going to be 8 pi squared over g squared. And because things are stationary, I'm going to have something that looks like del 2s del a mu del a nu. Delta a mu, delta a nu. So I'm expanding about the classical solution. So I'm writing a mu is a mu classical plus delta a mu. Okay. And I have here, because of this, the 1 over g squared this in my action. So remember, probably lost it. My action is s is minus 1 over 4 g squared integral f mu nu squared. Okay. For small g, okay, this term is suppressed in the integral here. Okay, so that's the nature of the semi-classical approximation. Small g, which corresponds to small h bar, okay, suppresses these fluctuations. Things are dominated by this leading classical result. Okay, that comes with several footnotes and asterisks, which we'll get to in a moment. Okay, so this is the kind of something about the nature of the path integral. Okay, and we're going to look then for these solutions. Okay, and these solutions are the things known as instantons. Sorry?
Is there an S classical missing in front of your H?
Probably. Well, here you mean? This is S classical. So my classical is a pi squared over g squared. Okay. So and I say this is, and what I've done here, I've used the fact that if I have a classical solution, that means that, you know, just as in your first course on Lagrangian mechanics, that means that the linear terms in the variation vanish. Okay, so we start out with terms that are quadratic. Okay, this is technically a sort of functional integral. Well, at least in principle, you know how to do.
But have you told us yet that integral, the possible action, is an integer?
No, I'm about to tell you that. So I'm about to tell you a little bit about these solutions. Okay, so I'm actually going to kind of write these down. Okay, and I'll tell you some of their features. Okay, so how might I look for a solution? Okay, there's a trick. So in general, okay, the Yang-Mills equations are complicated nonlinear equations. Okay, we can get at solutions here by noting that the object integral d4x f plus or minus f dual squared, okay, is the integral of a positive quantity. Okay, we're in Euclidean space, so I don't have to think about what f0I is and so on. Everything here is positive. And so this is greater than or equal to 0. Okay. And what does this look like? There are various pieces here. There's an integral d4x. There's f squared. So I'll put f mu nu squared here. Okay. And here I'm going to think about this, if I want. I can think about this in a matrix form. It doesn't really matter so much. Okay. But I have some kind of trace that I'm taking over these matrices. Okay. But there's a term that's a square. There's a term that's f dual squared. But f dual squared, I'll let you check, f dual squared is equal to f squared. Okay. So because of properties of this epsilon mu no rho sigma, or if you like, if I told you that f mu nu dual is like f mu nu with e and b reversed. Okay, so when I square it, I just get back what I started with. So I get this twice, and then I get plus or minus twice this object which has become an object of interest to us, f mu nu dual. Okay. So this object, which, as we said, is a total derivative, I think what Nima's alluding to, and we'll see more, is the fact that this is actually a topological object. Okay, it depends just on topological features of the solution, and small changes in f don't change it. Okay, okay, so what we learn from this is that we can bound our action. Okay, so in fact, what we can let you think this through for a moment, but integral d4x f mu nu squared is, let me write it correctly. Is greater than or equal to integral d4x f mu nu dual. And I'll put an absolute value sign in here because of that minus sign, okay, that plus or minus sign. Okay, so this object is bounded, okay, and the bound is saturated. Saturated, another typo here. If f is plus or minus f dual. Okay, and in this case, the the field configuration rather is said to be self-dual with a plus sign or anti-self-dual if you have a minus sign here. Okay, and clearly that's a kind of partly a question of how I define my epsilon, where I defined it to have what component I defined to be plus and which one's minus. Okay, so all right, so this is a condition that's first order. F mu nu is an object that's first order in derivatives, not second. Okay, and this equation is somewhat easier to solve than or in this form, the equation is somewhat easier to solve than in the case of the second order equation.
Is this the only way to saturate the bound? Like, could there be another point of saturation of the bound, or is that the place that is it obvious that's the only way that the bound is saturated?
Well, I think from this inequality, it's clear that to saturate the bound, to get 0 here, okay, those two terms have to cancel unless somehow they were both, I mean, they could both be 0. Okay, that's the sort of trivial configuration, the thing we build perturbation theory around. Okay, I think other than that, I think I have to get 0 here, I need to satisfy that equality. I have various experts in the room who can comment if there's something more exceptional, but I think that's correct. All right. So so let's write down, I'm going to just follow a tuft and write down a solution. Actually, these solutions were first found by Polyakov and collaborators. But I want to present them in a form, I'm going to present the solution in a form written down by Tuft, which is just rather compact and a lot of features can be seen easily. So Tuft introduced an object eta. So this is actually known usually as a Tuft's eta symbol. Okay, so an object eta a mu nu rho, eta a mu nu, I'm sorry. So it has 3 indices, 1 a group index and 2 space-time indices. Okay, and epsilon aij is, I'm sorry, eta aij is epsilon aij. Okay, and eta A4I is minus eta AI4 is equal to minus delta AI. Okay, and he introduced another symbol eta bar, which is equal to minus 1 to the see if I can read this correctly, delta AI plus delta A nu, eta, so this is A mu nu. Okay. So these symbols look a little weird, but in terms of these symbols, the classical solution looks like this. A mu A is twice eta A mu nu x nu over x squared plus some quantity rho squared. Okay, and this is the instanton. Okay, and if you, I should say, I'm sorry, I didn't say this. I'm working this out for SU2. Okay, for SU3, it's not much more work. Okay, so for this is for SU2. For SU3, maybe I'll just put this as a little aside over here. Okay, I can think of SU3 as just having an SU2 subgroup. Okay, and basically I can find these instanton solutions there by embedding this instanton I'm writing here, okay, in this SU2 subgroup, and then considering possible gauge transformations of that configuration, possible SU3 gauge transformations that rearrange this. Okay, so I'm not losing a lot of generality by writing down this SU2 solution. Okay. So, okay.
Would that be true for any gauge group that you find SU2 subgroups?
Yes. Well, I'd probably better be a little careful here. It's certainly for SUN groups. I'll be a little careful if I consider embeddings in SO groups and so on, introduce some new features, but roughly speaking, yes. Okay, and as that question hints, these instanton solutions are interesting to know about. They're not just relevant in QCD. They have broad implications in many areas of both of sort of standard model physics, but and certainly in thinking about quantum field theory and string theory and things like that more generally. Okay, so if I write down, yeah, let's see. The other thing I should write down is for you what F mu nu looks like. So F mu nu A is 4 eta A mu nu over x squared plus rho squared squared. And there's a rho squared up here. Okay. And this is just a straightforward computation with using the properties of this eta symbol to work out what the gauge field looks like. Okay. And what you need to know about this is eta A mu nu is a half epsilon mu nu rho sigma eta bar A rho sigma. Okay. So this F, as I've written it, is self-dual. It has this property that F equals F dual, like I said. Okay. So F equals F dual. And if I use the eta bar, if I replace eta by eta bar. Okay. So there are a number of things to notice about this solution. Okay. Among them, this A, the F, I should say, falls off very rapidly at large distances. So F goes like 1 over r to the 4th at large distances from here. Okay. But A, sort of as I promised, A goes like 1 over r at large distances. Okay. So A falls off slowly. Okay. The gauge covariant thing falls off rapidly. F squared or FF dual fall off extremely rapidly. But that current K mu I described does not. Okay? So that's sort of as we anticipated. Okay? And in fact, by construction, let's see. Yeah. Sorry? What was that? I couldn't hear it. Rho is a parameter, so rho is not fixed. Okay, so we're going to talk about this rho in a moment. Okay, so there's a solution for every rho. So I should, let me just say that here. Okay. And in fact, let me say a few things about these solutions while we're on this. So we have a solution for every rho. And this is because the classical theory has no length scale in it. Okay, so the classical gauge theory, we don't have quarks at the moment, and they're not important for this aspect of the solution. Okay, there's no length scale. So if we have a solution at one length scale, we have a solution at every length scale. And notice this solution has the feature that integral d4x f mu nu squared, and I'll put my quarter here. Okay, this is a number, right? I talked about how rapidly f falls off at large distances. This is 8 pi squared over g squared. Okay, it's this classical action that I wrote somewhere, that I wrote over there. Okay, it's 8 pi squared over g squared. Okay, and by construction, this is equal to integral. I'm sorry, by construction, this integral d4x f of dual is the same thing. So in fact, 1 over 8 pi squared, 1 over 32 pi squared, here, this I'll get the number right, this is equal to 1. Okay? So this is this thing, as I said, it's the integral of a total derivative, okay? But it's not 0 because of the slow fall off of the fields. Okay? And in fact, as I'll comment in a minute, it's actually, well, it has a, it's not only is it a topological object in the sense I described, but it has a meaning we can give this number some interpretation. So the fact that it's a number, okay, is not an accident. Okay, if for the anti-instanton, for the thing with eta bar, this is minus 1. Okay, so. Yeah, so let me say a few more things about this. So we have a solution for every row. Okay, we have also a solution. Okay, solutions at different points in space. So in fact, let me just fix that here. Okay, so here I've written it. This instanton essentially is largest in some sense at the origin. Okay, but the origin's not, there's nothing special about the origin. Our theory is translationally invariant. And so correspondingly, this solution, I can replace x nu by x nu minus x nu 0, some parameter. And here I have x minus x 0 squared plus rho squared. Okay. So I have solutions now for all scales rho. And I have solutions for all x naught, for all locations. Okay? And I'll refer to these things as translations of the instanton and dilations or dilatations of the instanton. Okay? And I also, it's a little harder to write it, but I've also, in writing things this way, I've chosen a direction. I've broken the O4 symmetry of the Euclidean theory, okay, the thing that we inherit from the Minkowski space symmetries of the theory. I've broken that O4 symmetry, and I can also consider rotations of this solution. Okay, I won't need those explicitly, so I won't use them here, but just to say there's one more coordinate, these are called collective coordinates of these solutions, one more symmetry which acts non-trivially on these solutions. Okay, so we have a whole set of solutions. And so we can ask, well, actually, yeah, let me say one more thing. I promised I would say something about the symmetries of this, more about the symmetries, what this topological object is measuring. And the way to understand that is to remember that if we think about our space-time symmetry, we have a symmetry SO4. Okay, we're in Euclidean space, so we have a Euclidean metric. The symmetry acting in the coordinates is SO4. And a group theory fact about SO4 is isomorphic to SU2 cross SU2. Okay. If you know about two-component spinors, you kind of know about that because those, in Euclidean space, those two-component spinor indices become either indices in one SU2 or the other. Okay, so the symmetry here is SU2 cross SU2. And this eta symbol, okay, which looks kind of mysterious, is really something like the following. It's related to a way of embedding the SU2 of the gauge theory in one of these SU2s. Okay? So in particular, eta A mu nu is trace A, sigma mu nu. Okay, now I'm using two-component notation. Okay, so sigma A, though, denotes now the group generators of the SU2, and sigma mu nu denotes the generators of space-time rotations in one of these SU2s. Okay, and yeah, and eta bar is something similar to half trace sigma A, sigma mu nu bar, okay, where this is the other. So those of you who are familiar, who suffer through a lot of supersymmetry, or say in kind of Wesson-Bagger notation, know this notion of these two sets of Lorentz generators, sigma mu bar. These are the Euclidean versions of those two, okay, and they reflect these two SU2 subgroups, okay. And what this is describing, if I look at asymptotically the field, so large R, A mu A, is twice eta A mu nu, x nu over x squared. My indices right. Hope I'm writing correctly, I think so. Okay, eta A mu nu over x squared. This thing is equal to I g inverse dig. At large distances, okay, the gauge field better not carry any energy. It should look formally like a gauge transformation, and it does, okay, where this G, and again, now I'm in danger of making factor of 2 mistakes, but G as a matrix looks like this. So I should say that, so I should write this as a matrix. So this is sigma A over 2. So this is as a matrix. This is, and this G is something simple. It looks like x4 plus I x dot sigma over square root of x squared plus sigma squared, x squared plus x4 squared. Okay, so that's something you can easily see as a unitary matrix. Okay, so if G dagger G is 1, okay, and this x dot, this whether I have x dot sigma or x dot or minus x dot sigma is a question of whether I embed in one or the other of these SU2s. So I'll let you do some of this if you're interested as exercises. Okay, you can check this.
Sorry, how does the Lorentz index?
I'm sorry, this should be mu. Sorry. So it should be A mu as a matrix looks like a gauge transformation of nothing, essentially. Okay? This is not true everywhere. This is a statement about the asymptotic behavior. And what this integral d4x k mu, d3x n mu k mu is measuring is the number of times you wind, as you go around a 3-sphere at large R, how many times you wrap around the gauge group. Okay? So that's that's what's going on here. Okay, that's kind of the geometric significance of this G. Okay? All right. So let's talk a little bit about what this means in terms of theta dependence and this U1 problem. Okay? So let's think first of all about the pure gauge theory. Okay, by that I mean no fermions, no matter. Okay, and so here I'm not asking about violation of the U1 symmetry. I'm asking about what is theta important. Okay, and so let's think about what the path integral looks like in this case. So here we have an integral. Let's call this z. Let's even call it z of theta. So I want to ask about this path integral, integral dA mu, e to the minus s, e to the I theta over 32 pi squared, integral d4x ff dual. And in general, I have some operator here corresponding to some correlation function I'm calculating or some expectation value I might be calculating. Okay? And so what do I know about this? I'm replacing a mu, remember, by a mu plus fluctuations. Okay. And so what do I have here? Okay. My S is 8 pi squared over g squared plus this fluctuation term. Okay. And this integral f of dual is plus I theta. Okay. So the integral I'm encountering here okay, so my integral, my z of theta, is equal to e to the minus 8 pi squared over g squared plus I theta. Okay, so that's the theta dependence I promised. Okay, so the action has some theta in it. And then I have the result of the integral over these fluctuations, e to the minus d2s dA mu dA nu times this delta a squared. Okay? Okay, so we have overall a factor e to the minus 8 pi squared over g squared plus I theta, okay, plus times rather some kind of determinant we get from doing this integral over the fluctuations. Okay, so what do we actually get? So if I take the instanton plus the anti-instanton, okay, I get z of theta is something involving cos theta e to the minus 8 pi squared over g squared times some kind of determinant. Okay, or since I'm doing bosons, I get some square root, 1 over square root of some kind of determinant. Okay, so I'm going to say something about the determinant in a moment, but I want to say here we've already now exhibited in a way, quite explicitly, we've exhibited this theta dependence. Okay, so so let's think a little bit now about what that determinant looks like, because that's also going to be interesting. So you could sort of say we're done. We've demonstrated theta dependence. But the problem is this calculation as it stands is not under very good control. And okay. And the problem is that, as I said, when I wrote down these solutions, I have these parameters x naught and rho. Okay. So if I calculate some object, what does the x naught do? The effect of the x naught integral will just be to restore translation invariance. Okay, so we start out, we have this instanton, it sort of sits at a point x naught, it's kind of localized, that's why it has finite action, it's localized at some point x naught. Okay, when I integrate over x naught, I'll restore translational invariance. So my Green's functions, for example, will be translation invariant. Yes?
So you already mentioned about the rotation of rotating the given solutions with rotam. How do you then restore rotations?
Those will restore rotations. In fact, what I didn't say, okay, just because this is not really, I have to apologize, this is not, you need, I will send you to various sources. It takes several lectures to really go through all this in detail. I want to give you some flavor and the feeling that you can fill in all the blanks. Okay, so for the rotations, so I talked about the fact that what we do in the solution is we sort of map one space-time SU2 into the group SU2. Okay? And as a result, in fact, these solutions have an invariance which is rotations in space times rotations with the opposite angle in the group. Okay? So there's one set of collective coordinates, one set of things which change this solution. Okay? And I'm not going to talk too much about those because that's a finite group. Okay? And I'm going to be focused more on rho and x naught. So the x naught, I told you, x naught involves an infinite set of things, okay? And so, but that has a rather simple effect. We're able to integrate over this x naught. I should say also, if you're really doing a path integral, you have to say, well, what goes on with all that determinant and stuff? You have to think about expanding the fields in modes, and you have to separate off these so-called zero modes, these modes which don't change the action because they're symmetries. Okay, and so for that you have to, there's some change of variables you have to do. Okay, but that's not particularly hard. And as I say, this is the effect of this x naught. The rho integral just is the angular integral is just finite, and it will restore rotation / global gauge transformation, global gauge symmetry. Okay, these are gauge transformations which go to constants at infinity. Okay, so that will restore those. Okay, and what's interesting is this scale size integral, this integral over rho. Okay, and what that's going to do, classically, is restore the scale symmetry. What does that mean? That means if I calculate some Green's function, some expectation value of some operator O with some dimension d, I'm going to get an integral, something which is this e to the minus 8 pi squared over g squared plus I theta, okay, times an integral d rho. Just to make up the dimensions, it's going to look like rho to the minus d, and I got to make my numbers right, minus 1. Okay, so it's going to look, so on dimensional grounds, it's going to look like that. If the operator has high dimension, it's going to be this expression looks like it might be very divergent at small rho. Okay, but what I have to remember is that this, I think I can put this here at this point. What I have to remember is that when I write this e to the minus 8 pi squared over g squared, I guess I should put it here. Let me put the integral outside. Okay. This g squared, okay, I have to tell you in QCD, I have to tell you what scale I'm evaluating g squared. And the only candidate here is rho. Okay, and when you actually evaluate the determinant carefully, as Tuft did in the late 1970s, okay, you indeed find that that's the case. So this is e to the minus 8 pi squared g squared of rho. Okay, and e to the minus 8 pi squared over g squared of rho, or an easy formula I like to remember, is 8 pi squared over g squared of some scale mu is equal to 8 pi squared over g squared at some reference scale m plus b naught, the lowest term in the beta function, log mu over m. Okay, so it's a sort of easy way to remember the one-loop solution of the renormalization group equation. That translates here into some e to the minus 8, some reference scale. I can just actually call this lambda to the b naught. And this becomes rho, I get an extra factor here of rho to the b naught. Okay, okay, so that rho, so what this does is turns this expression, b naught, for example, for SU3 with 3 flavors is 9. Okay, so that turns this expression into something that was nicely behaved in the infrared. Infrared means here large rho, large distance scales, into something that's badly behaved in the infrared in general. So unless the dimension is very large here, okay, this number diverges for large rho. Okay, so, and this is not really a surprise, since we don't really have a small parameter in QCD at our disposal, okay, we're just trying to calculate some random thing here. There's no reason why we should be able to do it. Okay? So the calculation, if you like, is dominated by large rho or by strong coupling. Okay? So what we have here is a situation where in the infrared, the coupling is strong and the computation breaks down. And this is the origin of my statement that this kind of semi-classical analysis, okay, this analysis where we pretend G is small or H bar is small, that this kind of semi-classical analysis, okay, gives us a clue that, in fact, this extra term in K mu that we talked about is important, okay, but we don't really have at this point, we don't have a reliable computation. Okay, so, all right, so, but we still have, if you like, some evidence that the strong CP, that theta, I should say, is a real parameter. Of QCD. Okay. Now, I want to talk a little bit now about, so far I haven't had quarks in the game, and I want to say a few words about what happens with quarks. Boss, what time am I supposed to quit?
Keep going.
He said it. It's his fault. Okay. So, I want to say a little bit about fermions, and once we say that, we'll kind of have really introduced both this U1 problem solution and the strong CP problem, and we'll be ready to take a break. Okay? So let's ask what fermions do in our functional integral. Okay? So in the functional integral, okay, what do I have now? I have my integral dA mu. But now I have my integral over quarks. This I might need here. I think I'm thinking of two-component fermions, dq bar. And I have what I had before. So I'll call it e to the minus s for the bosons. Okay. But now I have also my integral d4x, and I'm going to just do this for massless fermions, q bar d slash q. Okay. And now, when I do fermion functional integrals, well, I don't have a classical field at this point, but what I do have, so what I have to do, I have to develop q in modes. So I have d slash q is some lambda, qn is some lambda n qn. Okay. And similarly for q star. Okay. And when I do my integral, I get a determinant, I get a product of the lambdas. Okay. But what's special in this background are zero modes of this determinant, zero eigenvalues. Okay? Okay, because in those, when I say if I calculate something like, if I just try and calculate, for example, if the operator I put here is 1, if I put the unit operator here, then I'll just get 0. Okay, because right, I get a product of the eigenvalues. That's why I get a determinant. Okay, so I get 0. So I have to study, if I have 0 eigenvalues, I have to study operators which can soak up those 0 modes, which contain those 0 modes so as to get a non-zero result. Now, connected to this K mu are some number of 0 modes. And you can see that in the following way. So what we know is in the presence of the instanton, integral d4 x partial mu k mu, this is the thing that here I need a 1 over 16 pi squared. And let me put my NF, because my anomaly, my current, this U1 current involved the number of fermions. Okay? So this is equal to NF. right? Because that integral, this is this integral at f of dual, which is equal to 1, okay? And so what this says is in my instanton background, the charge should change. This U1 axial charge should change by NF, okay? And that, what does that mean in a Euclidean calculation? What that means is that operators which are non-zero, if the operator O, so let me put O in F, carries U1 a charge and F. Okay? So the non-vanishing Green's functions here violate the charge. Okay? That's something we really anticipated in this whole argument. Okay? And the way that works in practice here is that every fermion field, every fermion field has, and this I should say Q and Q bar, has a, am I writing that correctly? Yes. No. Yeah, Q bar, sorry. Has a zero mode. Okay. So in practice, for example, in three-flavor QCD, the operator that look at that, it's even clean still. Okay, so the operators which have non-zero vevs are things like this. The operator U bar U, D bar D, call that Y, S bar of Z, S of Z, okay, is not equal to 0, okay, because each of those fields, okay, has a zero mode in the instanton background, okay. So this violates, as anticipated, the UN asymmetry. Okay. All right, so what have we learned today so far? Okay, we've learned that QCD, well, we've asserted that QCD is an extremely successful theory, okay? And we've learned, but it has some puzzling feature. It has this feature that classically it has an approximate symmetry, okay? That approximate symmetry doesn't seem to be realized in nature, okay? We've argued that that's associated with this phenomenon of the anomaly, okay? And to argue that the anomaly has, well, and we said if that's the case, then this object FF dual, integral FF dual, which is a topological thing, it's the integral of a total divergence. We've seen something about what it measures, okay? And we've said that that object has to be important, okay? If that object is important, adding a term to the QCD Lagrangian theta integral over 32 pi squared integral d4x FF dual, that has to have physical effects, okay? And we've seen in one particular approximation, an approximation that in the end, for real QCD isn't reliable, but still it gives us some insight, and we'll see also there are other circumstances where it is reliable. We've seen that some evidence that the theory really does violate the symmetry. Okay? Now, I think people want coffee, so there are a couple of things I haven't gotten to, which were in my plans for this morning, and I'll do that this afternoon. Okay? I'll say a little bit more about the anomaly. I'll say a little bit more about this computation of the neutron electric dipole moment, mainly because I want to mention it because it doesn't involve, this calculation is kind of illustrative, but to say it applies to QCD involves some hand waving. I have to say something about this integral, wherever it went, this integral over rho, which is divergent, and maybe I cut it off or something. But we know enough about real QCD that we can say how large the neutron electric dipole moment would be if there were a theta present. And we can really establish this limit I described. Okay? So I'll say a little bit about that when I start this afternoon. And I'll also talk, and at that point, I'll list the possible solutions of this strong CP puzzle, at least the solutions that people, Nima and older, have thought about. And we'll start then talking about what's good and bad about some of them, which ones are more plausible and which less. That's the point where I'll kind of try and impose my prejudices upon you, which you then will spend the next few years of your careers on learning. Okay, so probably enough for today, for this morning.